standing for software-defined application infrastructure management and engineering. Now, I don't want to scare anybody with this long term, even us, even the project partners. We don't use the full name. We always use the Sodalite acronym just for the sake of simplicity. Yeah, okay. In technical terms, as I already mentioned, Sodalite is a project, a research and innovation project founded by the European Commission within its Horizon 2020 program. It's a 3-year project. We are actually nearing the end of this 3-year term. Actually, the official ending of the project will be just after the new year, so at the end of January. So we are getting ready to button the last details of our development. Yeah, basically our goal is to provide an optimized, resilient, and heterogeneous environment that can configure and deploy various applications on targeted cloud and HPC environments, and of course everything in between. Now, what this in between means, I actually have this tricky and complicated role of introducing the project without giving away too many spoilers, just because I don't want to, let's say, spoil the presentations of my colleagues that are following my presentation, and will be able to give you even more interesting and more technical details of what have we been doing in the past 3 years. So yeah, while we were developing, of course, we had to, of course, also prove that our developments are working. So the project is supported by 3 quite different use cases, I might say, which each individual use case is dealing and also using the 3 different let's say underlying infrastructures. So for example, we have a purely HPC use case, we have an edge and IoT use case, and a very interesting cloud use case. Now again, I won't go into details. There's going to be a presentation and demos of these use cases following my presentation, and I'm sure that all the presenters will give in-depth details of this. So just as a teaser and an introduction of what is to come. I apologize for those who don't like chemistry, but I've deliberately put this kind of periodic table here. It's a twist on the periodic table. It actually shows the complexity and variety of different DevOps tools that we have at our disposal every day. And of course, this is something that at least I feel brings, let's say, a little bit more complexity than necessary into our everyday job, and is also the reason why, or the challenge of Sodalite. When we envisioned Sodalite, we actually took a step back and said that the DevOps procedure doesn't have to be, or the DevOps workflow doesn't have to be so complex. We are dealing with applications where we are we are faced with the necessity for redundancy, fault tolerance, performance, reconfiguration for better performance, high availability. We have to provide and deploy different services, being typical cloud services or microservices running in Kubernetes containers, or maybe a high number of batched and queued jobs on HPC. And this brings another level of complexity because we have to face with different solutions and different architectures, being typical cloud architectures, stuff running in, as I mentioned, in containers, or jobs deployed on different queuing and scheduling systems, like on HPC with the Torque systems on Slurm or any other kind. Now, as I said, we wanted to take a step back. We didn't want to, or we wanted to abstract this approach a little bit, and we started from the premise that we don't want to touch the application. The application should be as its author envisioned it, and we don't want to touch the final infrastructure. So the missing link in between should cater both for the needs of the application as much as possible, of course, and it should fit everything to the target infrastructure, so that the solution is running as expected with the least amount of let's say headaches. While we were when we actually took this step back, we figured out that this missing link in between has actually sub layers or sub components or sub links within it, and each one in itself is its own challenge that if we tackle it one by one, we are able to deploy, or we are able to offer a complete solution. So we split this missing link, as I said, in between into 3 layers, so that each topic is covered to the best of our let's say ability. So in this modeling layer, we take a look at the application and at the infrastructure, and we model. We try to model in an standardized but still abstract way both the application and the final solution. This is then the input into the infrastructure as a code layer, where we define the infrastructure via software, and then this is then again the runtime input into the runtime layer, where we observe if the proposed solution is running as we want it, and if need be, we then do a loop and refactor and optimize to reach the best performance possible. Again, how this is done in details, it's coming in the following presentations. Yeah, to be able to provide this, we had to split everything into different actors, into different components and different processes. I'm just introducing here the terms that will be used in well, today during our session, just for familiarity. So we split the roles into different, we call them experts, that deal with resources, the application, the desired quality of the service, and we deal with different aspects of the infrastructure which interacts with these different actors in the whole process. So yeah, in short, the elevator pitch is that Sodalite is dealing, as I already mentioned, with modeling and abstraction, of both the applications and the resources. We try to be as tailored, but again, abstract, and we are doing a balancing act between the two. And of course, this balancing act is supported by semantics, by also in part machine learning and knowledge bases in the background. And of course, while we are doing this, we are taking a look at the complete life cycle from the design of the application up until the deployment, the running, and the optimization when it's actually running. Another very important approach or very important aspect of the project is that we don't want to live in our own bubble. We have been motivated by external people and by ourselves to reach out and to invite different initiatives and different projects to share their knowledge, share their opinion, share their experience to us. And we try to do this, of course, both ways. So we try to do an exchange of opinions and experiences. And I would say that this is something that mostly in the latter part of the project we achieved. So for example, and I just noticed that this slide is a little bit out of date because, for example, later on during the session, you will hear also from projects like PIACERE. RADON is, of course, here. There will be the project LEXIS. So there are some stuff that is missing here. And then, for example, in terms of collaboration, I have to expose also that we have contributed to the Tosca standard. XLab is actually presenting the Expo per hour solution to the Tosca technical committee. We have reached out to big and we have reached out and actually managed to deploy on big pan-European infrastructures like EGI and so on. So I think we are particularly proud that we were able to do this and to spread the word out. Yeah, I won't, since I'm running out of time, and I don't want to be taking the time away from others. Again, just we try to be complete, repeatable, standardized. We focus on performance and outreach. So in short, as I already mentioned, I have the most boring and the most let's say superficial presentation today. I will be followed up by many experts, which I had the pleasure to work with in the past 3 years. Following right behind me first is Joao, who will present. Well, the first thing that we will present is the exploitation and the business approach that we want to do with Sodalite. So we start with more the soft sciences, so to say, and then we will be followed later up today with, as I already mentioned, the demos, the use cases, and other projects and initiatives who think like us. And with that, I'm going to conclude For those who have your phones near and ready, follow us on different. I invite you to follow us on different social platforms, and if you need the QR codes for ease of access are here. And with that, I leave the floor to Joao.
Thank you so much, Nick. Joao, are you able to show your screen?
Good morning. I'm going to try. And yes, here it is. So you probably see my screen right now.
Yes, perfect.
Yeah, okay.
Presentation mode.
Very good. Thank you, Nate. Thank you, Anna. Thank you, all the present. My name is João Costa, and I'm leading the business development in Sodalite and representing its innovation, in which I'm going to present to you right now. If okay. So with this innovative technology, we enable simpler and faster development, deployment, operation, and execution of heterogeneous applications in HPC, cloud, edge, and software computing environments. This has been our let's say motto throughout to which we've been very consistent and supportive of. And so in the past 34 months, we have been designing the Sodalite product and building realistic business plans, building constructed on five well-defined key exploitable results, the Sodalite stacks. This layer-based approach is inspired both by the early development of Sodalite architecture and the good examples in the market that we are at, for example, HashiCorp. The innovation in the project is well distributed through five stacks. Each asset has usability and integrations KPIs as defined and followed by its assigned leader. In most cases, that's the IP owner inside of the consortium of satellites. The innovation track follows an IP perspective being classified between purely technical innovation or process innovation, putting pieces together that were not there before, or in the third one, which is diversification innovation, uh, meaning the refocusing on technology. The full stack solution has been exposed in many venues, leveraging the opportunity in the need of easing the work of DevOps experts, but also the data scientists that lack the expertise and resource flexibility, and need infrastructure and application optimization. This solution is supported by four layers, ensuring Tosca compliance through semantic intelligence, the appropriate security privacy policy compliance, targeting heterogeneous infrastructure, engaging the heterogeneous alliance, for example, and enhancing the quality of service, pursuing runtime performance optimization, and adhering to design time SLAs. Our first satellite stack is the Smart ID, from where the user interacts with the system, offering the SLA editor to develop the complex application deployment model, and the reasoner to provide recommendation validations with Tosca application deployment. This is particularly important because of the growing need of complex deployment in heterogeneous infrastructures, engaging a novel platform discovery service, cloud and HPC Tosca and Tosca compliance. The find IAC bug is the stack number 2 in Sodalite, using machine learning to address errors, smells, bugs in the infrastructure as a code, inadvertently introduced by DevOps humans, obviously. The ability to develop high quality, defect free, error free IAC code will be of great importance and is supported by data driven prediction on that code defects, smells, detections in ASC. We're going to see all this in action in a bit. To in what relates the third stack, mooring, so deployment, orchestration, and provisioning is focusing in which is focusing it's TOSCA compliant, overcoming the difficulty of manual deployments with light orchestration that is also extended to HPC environments. This enablement of HPC in this context is not yet present in the market, and or at least not so expressed, and can be a great advantage, having in mind the growing needs of powerful computation, for example, in deep learning. Um, the refit stack, so monitoring and reconfiguration, takes care of those tasks and capabilities in the Sodalite solution, addressing the problem of pinpointing applications that are causing problems and using the monitoring information to appropriately set the deployment options for a given context. With the growing complexity in the heterogeneous infrastructure, the value of such capabilities of monitoring infrastructure and redeploy applications and manage node resources becomes very important. And POET, our fifth stack, is responsible for the software-defined infrastructure, automating the optimization of application deployments for heterogeneous targets. There is no solution so far doing static optimization as such. This will bring automating optimization of application in HPC domain and for AIC environments, refactoring applications for performance, and helping application experts with limited hardware or optimization knowledge to use diverse targets in an optimal way. Um, To better understand the flexibility of Sodalite solution, we looked into the modularity of its stacks based on their dependencies, identifying great potential and reusing components. So the reuse is quite important for us. For example, in find IAC bug. But also in the compatibility of the system to adopt existing technologies and maintaining most functionality. On the other hand, we have developed integration with well-established technologies addressing edge through Kubernetes, clouds through OpenStack and AWS, ensuring coverage of open source and commercial projects, and HPC through Slurm and Torque, pursuing compatibility with common workflows. And we have also explored the potential of integrations with EGI, EOSC, and overall European initiatives for federated secure data infrastructure GAIX that we are addressing. Our business model offers an offer includes already available. It's already available in the end of the project, including on-premise installations, supporting a test bed trial, and we have discussed other options that will be further elaborated in the lifetime of the project. So the core differentiation between licenses will be based on limited features and deployments, and static dynamic application optimization capabilities. Some of these will also be addressed with premium services. Our early adopters are well positioned in the impactful areas: connected cars, in silico clinical trials, environmental efficiency, and Sodalite is helping them in improving infrastructure to enable better deep learning, preserving privacy in fleets and vehicles, or allowing for the virtualization of healthcare. The resourceful team underneath this great solution was built in the lifetime of the project, and the existing expertise and potential within the partners is key to the exploitation potential of these key exploitable results that we present. While industrial partners like will be leveraging Sodalite IP, the other other partners will actually be interested on other aspects, for example, on the resource and the challenges in research and so on. Right. So get to know Sodalite through the results published on the RADON results platform that will be updated very soon. On online news that we made available in big venues like HPC Wire or IPIC Info, and many inspiring events that we are present, like this one today. Thank you for that invitation. Our newsletter, blog, product page, and social media. We're very active on sharing our best practice and experiences and knowledge. Thank you for your attention. We'll be glad to answer all questions later on. Let us now have a look at the product in action.
If anybody has any question, take it out that you can ask on the chat that you will see on the right side, and then the floor goes to Giovanni, who will present the demo.
Thank you, Anna. Thank you, Al. So let me share the screen. All right. Are you able to see my screen?
Put it in presentation mode. Okay.
All right. I'm Giovanni Quattrocchi. I work as a researcher in Politecnico di Milano. And I'm going to show you almost the full Sodalite stack in action through an end-to-end demo. So, the Sodalite stack was already introduced by the previous presenters. Just to tell you that this demo will cover the first 4 layers of the stack. So smart ID mooring, so how we can deploy a model. The find the bug for understanding the smells that could affect the model, the application model built. And if there will be time, a bit of also runtime reconfiguration that we apply during the execution of the application that was previously deployed. In order to give you this demo, I'm going to use the snow use case. So the snow use case, one of the free use cases using Sodalite. And basically the idea, the goal of this application is to provide a water availability indicator through the analysis of images of mountains, which are gathered through 2 different streams of data. The first one comes from a set of webcams, so images from webcams, and the second one through, let's say, public images repositories, such as Flickr. And so these inputs are processed through, let's say, a small pipeline in order to filter the images that are not actually important in this process. And then the 2 inputs use a data pipeline mainly based on machine learning, but also image processing, which is composed by 5 components that are applied in a sequence. Most of the use case use cloud machines, cloud virtual machines, or cloud deployments. But for the ML training of some of the components, HPC could be used. In the demo, we are only going to see the, let's say, cloud part. The deployment that I'm going to show is quite simple. Of course, it can be generalized on much more complex ones. And it was done in the Sodalite testbed. So we have 2 virtual machines, and as you can see, we have several components deployed onto those machines. Each white rectangle is a container. And here we are not showing some additional components that are deployed, such as volumes. We have some, containers that are related to computations, other for data storage, for example, MySQL. And mostly the components are deployed in the first virtual machine, but in the second virtual machine, we have fewer components, but let's say more computational intensive. This is why it's a bit asymmetric, this deployment. So here, the idea is that the application ops expert defines a abstract application deployment model, AADM. And this process involves the knowledge base where the resources are stored. The resources are, let's say, the types of the components, the abstract type of the components that can be used in specifying the model. In addition to that, which is not shown in the demo, there is another flow which involves the creation of component container images, which are stored in a, let's say, public or private registry. And after that, we have the generation of a Tosca blueprint. So we are using a slightly different syntax for defining AADM, but then it's translated into Tosca blueprints. And basically, there is an analysis while we do this process of the blueprints and the Ansible code if used that compose the deployment model, as I will show you. So the components involved are the Smart IDE for the definition of the AADM and the generation of Tosca blueprint, and also the find Yak bug analyzer in order to understand which are the smells that could affect the deployment created. For the creation of the component images, we have mooring, or that is part of the, and in particular, one component of mooring that is the image builder, which creates, again, the component images. For the optimization of the code and the container images, we have Poet, which is not shown in the demo. So what I'm going to show you right now is the Smart IDE and find Yak bug component in action. So let me start this video. So this is the IDE. We have mostly two main panels. The central one, where we can find the, let's say, textual representation of the AADM, which is the main panel that the application ops expert will use. And we have the graphical one, which basically is another representation of the AADM. The expert can either modify or, write the model using the textual or the UI-based editor. And the editors, of course, they are in sync. So one change in the textual one, for example, is reflected in the graphical one. We are going to start from an almost complete model of the application, in particular of the Snow application. And so as you can see, basically the syntax is very similar to the Tosca syntax. Is again based on a YAML-like language. And basically, in addition to this main panel, we have on the left-hand side an outline where all the components or the parts of the AADM are shown. And we can navigate the AADM through this outline. Skip a bit. Sorry about that. All right, sorry about that. I was saying that, okay, here we have the textual model. Again, we have the UI representation on the right. So we can navigate the UI representation. The UI representation is mainly used for communication purposes, but it also provides means to modify the AADM through these property view. So when we select one element below in the bottom part of the editor, we have the possibility of changing properties. So as you can see, there is, let's say, a reflection and a sync between the two representation. And so the idea is that we want to modify this AADM by adding a new component. And to do so, we can use the assistant editor that is provided by the IDE. So in this case, according to the indentation level that we set, we have a suggestion. In this case, the suggestion was to add a node template ID, so a new component, the name for the new component. And then we have to specify some either properties or attributes for this component. In particular, the first thing that we have to specify is the type. And if we type type, basically we have some suggestion from the knowledge base, and we selected basically the Dockerized component since the component is a Docker-based component. And as soon as we save the AADM in the UI-based representation, we have the component added, and we can do a similar process by using the palette of the UI-based editor by dragging and drop a new component and modifying this component through the property view that again is shown in the bottom part of the IDE. So in this case, we are creating two new components, one with the textual editor, one with the UI-based editor. And as soon as we save, basically the component that was created through the UI is added to the textual representation. And of course, we have already seen the opposite flow. So if we remove the new component and save, the new component in the UI disappears, and so on. So let me skip a bit. So something that we can do is to, for example, stop here and save in the knowledge base this AADM. And as soon as we save the AADM in the knowledge base, we will retrieve a, let's say, report, in this case, an error report, which says that there are some problems, syntactical or mostly semantic. And in this case, the problems are multiple. In particular, we miss some properties and some requirements. So it says that we miss, for example, property image name or registry URL, and also some requirements. So thanks to these suggestions, we can again ask the assistant to help us in writing the this YAC. So we are adding a property. So image name, And in this case, we are selecting a, let's say, publicly available NGX image. We have to specify also an alias. These are, let's say, implementation details, but these properties are required by the type, so the Dockerized components. So we have to specify them. So if we continue, we have to specify a registry URL. And in this case, we want to read this value by the inputs that are provided when we deploy this AADM, as I will show you later. So in this case, we are using the keyword get input with a name of the input that was defined above in order to read this parameter, while image name and alias were, let's say, are coded. So now we are again saving the AADM in the knowledge base. And again, we have an error because we didn't specify the requirements. So let's add the requirements. So we have to specify a host requirement. And as you can see, as soon as we type node, we indicate that there is like a link between two components in the AADM, and the knowledge base suggests us the possible compatible components that will fulfill and meet this requirement. So if we save again, we should have probably an additional error. Yeah, so we still have an error because we missed the requirement registry. In this case, we use the suggestion from the IDE assistant. So we didn't type anything. Basically, we use autofill. And now if we save in the AADM knowledge base, well, we won't have any additional error. So as you can see, the flow is quite easy and assisted by the IDE. Also in the UI representation, we have these checks that indicates that the requirements are correctly fulfilled. And finally, in this, we have an additional panel in the bottom part of the editor to browse the knowledge base. So if a user wants to check what is available currently in the knowledge base, we can use that view, this view. And this view contains both the resource models and also all the AADMs that were saved by the users in the knowledge base. So in this case, we have plenty of AADMs already created. So for example, for the Snow use case, we have multiple. And that's it for the IDE. The last part is related to the smells. So actually, I can skip a bit here. So when we save the AADM in the knowledge base, we retrieve not only errors, as we have seen so far, apart from the last saving process, but also warnings. And these warnings indicate a possible smell in the AADM. So if we take a look at these warnings that are specified in, that are shown in yellow color, for example, this one refers to the fact that the address that we specified is not static. Or, for example, another one is that the username for a component is either root or admin. And one of the exposed part of the container is outside the range that was specified in the property above. So this was a very quick demo of how we can also have, let's say, semantic hints on what may be not correct in the AADM. So after defining the AADM, what we can do is to deploy the application. So this is shown through this additional video. So as soon as we have the AADM completed and without errors and possibly those without warnings, we can right-click on the AADM and then select in this contextual menu, deploy AADM. So we have to provide some inputs, but also in this case, the process is quite straightforward. So we have to specify the deployment name. So for example, Snow 0001 deployment, an optional version tag, the number of orchestrator workers that will be involved in the deployment, in this case 1, which is the default value. We can also use the image builder to create dynamically, let's say, during the deployment process, the container images, if needed. And finally, we have to select an input file for, let's say, materializing all the inputs that are basically the parameters of the AADM that will be used during the deployment process. So we can select a file through the, let's say, local computer explorer. This file is a YAML file, and it's a key value file, very simple one. And basically this view is then filled with the value read from the files. Of course, this view, which relates to the inputs, is dynamic in a sense that if we change the inputs in the AADM, also this view will be slightly different. And well, the inputs in the case of the Snow use case are various. So we have, for example, metadata regarding the Docker configuration, so the name of the network or the credentials and the URL of the Docker registry where the Docker images are stored. We have the flavor name for the virtual machines that are used in order to, the two virtual machines that are used for deploying these AADM. The virtual machines come from the OpenStack environment. While we have some credentials again on regarding database, the databases that are used in the AADM. Again, we have also a network name for the OpenStack and security groups. And finally, SSH key name and username in order to being able to connect to these virtual machines through SSH connection. So when we review these, after reviewing these inputs, we can proceed with the deployment. Simply by clicking deploy. And well, the process lasts a bit, and it starts by, again, saving the AADM and checking that, there are no errors. And then after a while, we will get the like a confirmation message that in this case the AADM was successfully deployed into the Sodalite testbed. In this case, we have some IDs in order to being able to refer to this deployment. And then we can select in the bottom part of the ID, the so-called deployment governance view, where all the deployments are stored. You have to refresh them. And the last one, since they are ordered in chronological order, is the one that we just deployed. So if we click on it, we will retrieve some, let's say, useful information regarding deployment. So again, the IDs, the state, which was successful. Instance state is the state, the internal state of each component that was deployed in the virtual machines. Monitoring dashboards, which will be shown in a few minutes. Again, we can check the inputs used just to have them stored somewhere. And we have some timestamps, and we have the console log, both standard out and standard error. In this case, only standard out because we didn't have any error. And well, if we click, we can see the log of the deployment. So if we go back to monitoring dashboard, we have a link. In this case, is I mean the dashboard is deployed under a VPN. But yeah, if we click on the link, we have the monitoring dashboard, and we can see some, let's say, metrics regarding the 2 virtual machines that were deployed. So as you can see here, we can select between the 2 virtual machines. We have the, for example, CPU utilization, the space used, the memory, and so on. So this provides a, let's say, nice overview of what is going on into the machines. And of course, we have SSH connection in order to do something more let's say, ad hoc. So this ends the deployment part. And all right. So after the application deployment, then Sodalite applies some, let's say, optimization at runtime. This is done mainly by 2 components, the deployment refactorer, which is not part of the demo for lack of time, and the node manager. So the first one, so the deployment refactorer, is basically used for changing the deployment according to various metrics, and it more or less, in terms of resources, provides horizontal scalability for the application. So if an application requires more virtual machines, for example, the deployment refactorer will add those needed virtual machines. In the demo, we are going to see the node manager, which provides 2 main things. So first of all, the node manager works with a heterogeneous cluster of resources. So virtual machines or physical machines that have both CPUs and GPUs. And we assume that the applications that are running can exploit both these resources. Of course, it works also for applications that use only CPUs, but the main characteristic of the node manager is that it supports heterogeneous resources. So the node manager schedules requests of the from the users to one of the possible devices. So one of the GPUs or one of the CPUs, according to some logic that mainly regard the current application performance. So the assumption here is that each application is constrained by a response time service level agreement. And therefore, the GPUs are used mostly for applications that need like an acceleration in that moment. And on the other hand, CPUs are used for all the remaining requests that could not be fit in GPUs. And we have control theoretical planners distributed in a cluster that basically continuously reallocates these CPU resources in order to meet the SLA violations. So the idea is that we have vertical scalability for CPUs and scheduling for GPUs. So I'm going to show you an additional video. Okay. So this experiment was run in a slightly different setup. We use a public cloud in order to have GPUs and CPUs in the cluster. At the time that we ran this experiment, this was not possible in the testbed. And we are using two applications that are deployed in a cluster, as you can see, that was deployed in Azure, in the public Microsoft cloud. So these virtual machines have 6 cores and 1 GPU each. And these two applications, one is a Skyline extractor that comes from the Snow use cases, one of the components that was mentioned before. And the other one is a well-known neural network, GoogleNet. So the idea is that these applications have a different workload, meaning that we will have a peak at the beginning for GoogleNet, which is followed by a peak in Skyline extractor. Of course, these are synthetic workload, but I mean, the node manager was for mostly any workload shape. The workload will be intercepted by the dispatcher that dispatches requests according to the performance of the applications. And then in each node, we have the control theoretical planners that are PID controllers, actually, that continuously rescale the CPU resources to these applications. So let me go to the experiment. Okay, here. So apologies if it's a bit too small, but we have 4 charts here that are dynamic. I just stopped the video. So the first one is the response time. And in the chart, you will see 2 curves, one for Skyline extractor in green and one for GoogleNet in red. And these horizontal lines are the SLAs. So in green, again, we have Skyline. This is the SLA for Skyline. And in the dark red, we have the SLA for GoogleNet. So the idea is that the response time should be almost always below these horizontal lines. Then we have the second chart that is the workload. So how many resources are incoming in the cluster. This is aggregated. I mean, we have 2 virtual machines, but this is an aggregated dashboard. We have a third chart that counts how many requests are dispatched on the GPU for both the applications. Again, green for Skyline and red for GoogleNet. And finally, the last one is how many cores are dynamically allocated to the 2 applications. So let's start the, yeah. All right. So the experiment started. So at the beginning, as you can see, the 2 workloads are very, similar. The core allocation is almost constant. We have some fluctuations, but let's say everything is under control. We have mostly a fair allocation for the GPUs. And at this point, we have a peak in the workload of, and with few seconds. So each tick is 1 second. It's happening, let's say, in real time. So we have few violations, but as soon as you have a violation, we increase both the number of requests executed on the GPU for GoogleNet and also the core allocation. As you can see, it's much higher here for GoogleNet. with respect to the green line. And then starting from this point, we have a peak in the workload of skyline extraction. And again, same story. So we have a small violation, which is followed by a, let's say, a reaction, both in terms of GPU scheduling and also core allocation. Of course, it's not symmetric completely because the two applications have a different dynamic, but in the end, the behavior is the same. So after the peak is the peak for skyline extraction is terminated, we have a moderate workload for both, and the GPU allocations becomes it was fair as the core allocation. So that terminates the end-to-end demo. So if you have any questions, I will be happy to answer.
Thank you so much, Giovanni. Very interesting demo. I don't know if there are not any questions, then we can move on to the next presentation. We're just a little bit behind in the schedule. So maybe we can go to Paul's presentation, and if you have any question, you can do it on the chat, and then Giovanni can reply via chat.
Sure.
Thank you. Paul, are you able to share your screen? You're on mute and we cannot hear you. No, I don't think his mic is working. Okay, so then let's start with Ralph Schneider's presentation on the in silico trials use case, and then we can go back to Paul once he's able to connect. Okay, perfect, Ralph. We can see you. Can you share your screen, please?
Yes, and I hope you can hear me.
Yes.
Yes, perfect. Let me share my screen. You can see that now?
Yes, perfect.
Yes.
Thank you.
Yeah, welcome also from my side. Wait a moment. Go to full screen. Yeah. Yeah, I will show you one of the 3 use cases in the Sodalite project. This is the one we call the clinical trials use case. And what we deal with in this are virtual clinical trials. And they deal basically with the evaluation of medical devices in our case, and maybe also other virtual clinical trials for drugs or stuff like that, but we deal with medical devices, as you can see here. In the simulation, it is nicely possible to evaluate different implants within the same patient and evaluate their performance. Here, this was done with hip implants in the human femur, but in Sodalite, we are dealing with this medical problem, which is the so-called fusion of the lumbar spine. You can see my mouse, right? Yes. Here you see the lumbar spine, and if there are severe problems with the intervertebral discs, like you can see here, this dislocation of these 2 vertebrae, then this is fixed by a fixator system that is put in place, and also with these cages here that put the vertebrae in place. As you can see here in this cross section, here you see these cages. And what we are trying to do with this simulation is we are trying to support medical device manufacturers, but also surgeons in development of these types of implants. because currently nowadays these implants are developed on an empirical basis, and the quantification of the performance of such implants in large patient groups in detail is not really easily possible, and this is what we are now trying to achieve with simulation. For that, we developed a process chain, a simulation process chain that is composed out of several components. Currently, we have 7, basically. First, we have imaging data from clinical CT scanning. Also, X-ray data are incorporated to position the patient correctly. From these imaging data, we extract the surface of the bones, as you can see here. What then has to be done is further discretization of the geometry. For example, we have to put in here the intervertebral discs. What has also to be done is volume meshing. So here you only have the surface mesh. In the next step of the discretization, we also do volume meshing. This volume mesh we have to enhance with additional features that can be recognized here. For example, these tendons, also tendons in front of the intervertebral discs. Once this is done, we do what we call material mapping. That is done by a probabilistic mapping component, which is based again on the imaging data. From this, we get a model with an inhomogeneous material distribution that represents the patient-specific distribution of the bone density. That is very crucial when you insert screws and such fixation devices in the bone. And based on this complete model, then we do a simulation, a finite element analysis of the structural mechanic characteristics of the complete bone implant compound. Here you can see a result of such a simulation from the outside, and here a cross-section through the intravertebral discs and the 2 vertebrae that were considered here. All the components of the use case process chain have different runtime behavior. They communicate basically via the file system. So what you see here are basically the blue rectangles are the data representation, and written above here are the components that are implemented in different programming languages and with different techniques. For example, the probabilistic mapping component is an MPI-based program. So is the solver. All other programs are basically serialized programs, but sometimes have heavy memory requirements. This is why we have here 2 requirement areas for the components. So the first components can run either on the cloud or on the HPC. The last 2 components, so the probabilistic mapping as well as the solver, we take the open source finite element package code Asta as a solver. They will be run best on HPC because they are parallel programs and they require quite a bit of parallel computing resources. So our requirements are an infrastructure that is able to deploy the scientific workflow composed out of multiple integrated components in an efficient way over heterogeneous hardware infrastructures. Since we are currently developing this on bare metal, deployment is quite tricky, quite hard, especially installation of the solver component is not that easy for unexperienced users. And but if we deploy this then on heterogeneous hardware, the efficient development and failure management becomes crucial, right? Because the unexperienced user that who is developing this process chain from a theoretical point of view, so from the structural mechanic point of view, is almost every time not able to have a detailed idea about the underlying structure of cloud components, HPC components, and stuff like that. So failure management in the deployment and stuff like that, debugging features are quite crucial. Yeah, data processing tasks are not finally defined, but may change and get complicated, especially if we regard this virtual clinical trials. So what we are do is not only execute one simulation, but several simulations on different patient data sets, and then evaluate the performance of the implants in the given patient. So efficient uncertainty quantification, which is currently basically done manually. This is what we need for this component. And of course, if you then take the whole process chain a step further and think about what if this is really going to be operational in a hospital, then of course efficient execution in times of time, cost, and power becomes crucial, because then of course somebody has to pay for the computing time, for the computing resources, and then this becomes urgent. Yeah, as said, the current deployment methodology is not very productive, right? So the process chain developer has also to deploy. This requires effectiveness in deployment. The management of the adoption to different hardware infrastructure is basically offloaded to the user. And as said, the users are not the most experienced when it comes to the handling of HPC systems, cloud infrastructure, and stuff like that. So development DevOps are definitely needed for this kind of use case to reduce costs and effort, and also the portability of the complete process chain. Yeah, what was done is we used the IDE to do the smart modeling. We have also a YouTube demo of the IDE available. And the workflow modeling you can see here. There's also a full description of the IDE on GitHub, and of course this was just demonstrated. Yeah, the modeling is quite straightforward, and what was really an improvement with Sodalite was that the modeling of the component interaction was more simplified, right? And since the user can select whether the component runs on the HPC or on the cloud component, this is really useful for the user, because what can be found now on GitHub and Docker Hub is are optimized containers. So experts can take over in the optimization of the containers for the given application, for the given component of the workflow. And then the user can simply use this and deploy it on whatever component its resources require. Yeah, so the effort reduction for the deployment of the code was quite nice to have. And the adaptive optimization of the components to different targets, like, for example, different MPI implementations, this was also achieved. In terms of exploitation, what we will do with this use case after Sodalite, the developments we used will directly enter our research activities. With respect to the implant development, we have currently a project running that evaluates bone screws, the strength of bone screws, and there we can directly use the developments done in Sodalite. The principle and components with respect to data access are also extremely helpful, because this is always kind of a problem when data centers interact with hospitals or clinical data providers. There's always this problem that the data security is not always compatible, right? And with the data handling components in Sodalite, we think this will be quite ease the situation. Also we will push the ideas forward via the Medical Solution Center. This is an activity of HLS and the CCOS BW company, which promotes HPC to SMEs in the area of medical device manufacturing and medical engineering. And with that, I'm done with this short presentation of this use case. And in case you have any question, I'd be happy to answer.
Thank you so much. Very interesting to see how we're using Sodalite in this environment. Any questions from the audience? People are a little bit shy today, so let's see if they ask something through the chat. Paul, maybe you can present this time. Can you please try unmuting yourself? We can't hear you. Yes, let's start with you, Pedro.
So it's my turn?
Yes, because Paul is not able to unmute himself. So.
Okay, ready, steady, go then.
Yes, and then we'll leave Paul for the end. Thank you.
So let's have a look at yet another use case in a quite different domain, in the domain of fight against environmental crime. The idea started from the observation that there are many Earth observation products from satellites, but they don't address all the potential scenarios and use cases that you may have in environmental monitoring. But at the same time, there is a lot of public web content that is produced either by people in social media or content sharing sites, or also by, let's say, automated ground sensors, such as, for example, touristic webcams. So if you have to observe some environmental phenomenon below, for example, the cloud cover, the problem that we wanted to address, the question that we wanted to face was whether this content that is massive, very well distributed both spatially and temporally, can be exploited to extract some knowledge that could help people address environmental problems. This idea was applied to a specific application that is water availability prediction. And the idea is that in mountain-dominated regions, most of the water supply comes from the snowpack that is stored on top of the mountains. And if you're able to predict the amount of water that you will have during the dry season, there are several optimizations that you can do in territory management. For example, allocating water optimally between different uses such as agriculture, civic uses, and hydropower and the like. And so our idea was to understand whether we could use user-generated content, mountain photographs posted on social media sites or content sharing sites, but also the images that are daily produced by touristic webcams in mountain resorts, acquire them and extract some knowledge from them that could be used to predict some meaningful index correlated to the amount of snow, the depth and quantity of the snowpack that you have in the mountain tops. And with that, being able to predict how that snow mountain pack would affect the availability of water. So the input to the use case is quite heterogeneous. It's a set of images that are being crawled by, let's say, in nowadays less popular but still very populated content sharing site that is Flickr. And then we identify more than 2,000 webcams distributed over the Alpine region, some of them acquiring images at a very high frequency. And from there, we crawled kind of 10 million images. And the input is not only visual, because as I will discuss, you also need to register some of the images that were taken by the user with respect to the position on the Earth globe where they were taken. And so another input is a digital elevation model of the planet, which is essentially a big repository of numerical data that represent as a point cloud the surface of the Earth, which is especially useful in mountainous region in order to understand what are the mountains that are portrayed in a given image. And the output is a set of what we call virtual snow indexes. For example, one of those indexes is the minimum altitude at which you see the snow level in a given mountainside, which are proxy to the physical quantity that people measure with ground station that is called the snow water equivalent. That is the amount of snow that would probably turn into water in the dry season. So in order to, let's say, test this idea, we had to set up a quite articulated workflow, a pipeline made of several components, as in the previous use case. Again, one of the characteristics of this use case is the high heterogeneity of the component that do different things and have different requirements and constraints. Essentially, the workflow has a common final, let's say, stage and two data acquisition legs. One is for acquiring images from public content sharing sites, and this requires crawling content sharing site or a social media platform. And then this crawling is based on a simple, let's say, keyword search, which may obviously produce a lot of garbage input. The crawling is followed by, let's say, a relevance classification step in order to eliminate all the images that were tagged with an apparently relevant keyword, but that are not actually portraying a mountain profile. The second leg, the secondary acquisition leg, instead, is the pipeline that fetches images from webcams. And most of the webcams that are installed in touristic locations are, let's say, are publishing a URL where you can, at a given frequency, acquire the acquisition of the webcam. And in this case, the acquisition pipeline is slightly different because you know that the webcam is portraying a mountain, so you don't need to filter for irrelevance. But at the same time, since the temporal frequency is very high and the webcam is not an intelligent agent, it may take photos also in bad weather conditions. There are other, let's say, filtering steps in order to get into the system only images that make sense. Then when this large set of images has been acquired, there is, let's say, the final stage of the workflow that is actually extracting the knowledge that is needed in order to produce the virtual snow index. If the image is not registered to the Earth surface, it must be geolocalized, and this can be done with the digital elevation model of the Earth. Then each image is processed in order to extract the visual snow information, and then the visual snow information with some computational geometry is processed in order to extract, for example, the minimum altitude at which snow is appearing in each image. Just to give you a quick impression of what the workflow actually does, this is the branch that is acquiring images from webcams, and that applies a weather filter in order to, let's say, eliminate from the acquisition all images that were taken during snowfall or rain or in cloudy conditions or fog conditions. But then there is also another more subtle problem. There is the fact that when you are taking images at different hours of the day, the luminance condition may vary, and so images may have very different visual appearances in different times of the day. And so another step that makes the input more robust for the subsequent analysis, since typically the snow indexes are extracted once per day, is to make a kind of a daily image median, which is a median, an average image that let's say, considers all the images taken in one day and collapse them into a single image with the optimal visibility. Another process step that is using quite different means instead is the process that extracts snow mask information from an arbitrary mountain image, which seems to be a simple problem, but it's not like, let's say, detecting white pixel, because due to lighting condition, the same color may represent very different things based on the position and the context in the image. And so we trained a snow detector in order to be able to transform a natural color image into a binary image where the white pixels are, let's say, with high confidence representing snow. From the snow mask, then we compute virtual snow indexes. This is just one of the output that shows how the red line, which is the minimum altitude of the snow that we compute from crawled images from mountain webcams, follow the temperature line, which is the black one. As you see, the two paths coincide pretty well with, as expected, some hysteresis, some delay between the snow altitude diminishing and the temperature increasing or decreasing. So besides, let's say, the meaning of the application that is quite specialized for environmental agencies, but the point that we felt would make it interesting for a project and a technological effort such as Sodalite is the fact that the pipeline, again, is extremely heterogeneous. Some of the tasks are CPU bound, some other GPU bound, many are IO bound because we are shipping images all around the place. And so an intelligent partition of work that considers the amount of images that you have at hand at a given moment during the processing and dispatches them to the most, let's say, available node would obviously be very much beneficial to the throughput. Some tasks also use deep learning. Some of the classifiers now have been implemented with deep learning, which is a hot topic for both training time and runtime optimization. So we felt that this use case was quite a good benchmark for an architecture that would provide an optimized and power-efficient use of the available runtime resources. And the goal that we have at the end of the project is to increase throughput by, let's say, the same amount of runtime resources, obviously, but not only throughput, which is the number of images that we can process per second, but also the classification accuracy and the representativeness of the virtual indexes, because if we can process more images, we can also probably end up with more, let's say, significant input to the pipeline. So far, as Giovanni has discussed in the end-to-end demo, we have been testing the benefits of the Sodalite platform in various ways. One, it has been already declared, is the fact that you can model the pipeline at a high level, which is something very beneficial. I will mention later on who are the target users, but typically they are not people that are able, let's say, to specify a workflow in a highly technical manner. The runtime tests that have been conducted so far demonstrated the fact that the SLA is very much preserved by having a node manager that can listen to the use of runtime resources and, let's say, manage allocation in a clever way. And with the same amount of resources, we observed a speed up and even a significant speed up by using less resources than in, let's say, the naive implementation that was the baseline that we had implemented before the start of the project. Obviously, one of the future objective would be the possibility of easily setting up declarative alert specification in order to configure a situation where, for example, the pipeline should split some of the component and allocate more capacity to them, or either reduce the occupancy of runtime resources, for example, because some of the webcams have been put offline, which is something that happens. You can imagine with 2,000 webcams, how dynamic is the content acquisition step. So there are many potential benefits that one can reap if there is an intelligent allocation of resources based on runtime condition. We are only, let's say, starting to reap these benefits. We are gonna complete by the end of the project some of, let's say, the goals that we have set to ourselves, both on, let's say, the machine learning training part, where we are experimenting with APC and MODAC, but also on the actual management of the pipeline itself, especially as far as the movement of data is concerned among the various nodes. Because again, if you, let's say, increment the number of nodes, then you may have an overhead in shipping images, which are, I mean, bulky here and there across the runtime architecture. We still have to apply the node manager to all the components, and so to make a quantitative evaluation, not only for the more, let's say, CPU and GPU intensive one, but through the entire pipeline. And then we are waiting also for the last deployment of the AI-powered alert functionality, where interesting alert may be discovered by observing the log of the execution itself. Exploitation is already ongoing because this, as it may appear, is quite a fancy application. We are not aiming at replacing the snow stations that are deployed in the Alps. It was an attempt to demonstrate that you can use a public web content as a proxy of snow monitoring station in regions where you don't have such stations, which are the majority, for example, in the Alpine region. Only 120 snow monitoring stations are deployed in Italy across the entire Alpine spectrum. But we have already signed a memorandum of understanding with one public administration, the Environmental Agency of Region Lombardy, for a different pipeline. In this case, one that is not experimental, but it is already in use, but should be recasted into a more intelligent form, that has to do with environmental crime monitoring, specifically geospatial intelligence pipeline that is going to detect from different inputs the presence of illegal waste dump and landfills. The, let's say, architecture that let's say we have deployed in the project is archetypal. Many other, let's say, environment monitoring applications share the same philosophy, receiving multiple heterogeneous input and processing them through stages application that could be distributed in a hybrid, let's say, runtime network, including both APC and cloud components. As a final note, we have observed that we are going to target public administration mainly. We are a public university, and so they are our, let's say, partner of choice. And the fact that you would be able, via modeling and code generation, to lower the technical barriers for, let's say, setting up such kind of data acquisition and processing pipeline is very instrumental to the so-called technological transition that these agencies are requested to do, because the skills that they possess are very high in their respective application domain. water availability prediction or photo interpretation for, let's say, illegal landfill detection. But at the other end, the DevOps skills that they may put on the table are rather limited. And so we think that there is an enormous space, business opportunity for any solution that would be able to lower the technical barrier for this kind of application. And this is it essentially. So you have seen in part the pipeline already running in the preceding end-to-end demo by Giovanni, but I'm still, let's say, available for responding to any other question. And thank you for listening.
Again, a very interesting example of how we are using Sodalite. Paul, let's give it a try. Third time's a charm, so let's hope this time is working. I think we can hear you.
You can or you cannot?
Yes, we can. Positive.
Oh, you can. Okay, great.
Great.
It's unexpected.
Okay.
All right, I will try to share my screen then.
Yeah, perfect. We can also see you.
Okay, so hopefully you can see the slides.
Not yet.
Not yet.
No.
Again.
Let's do something. I have your presentation, the one that you uploaded, so I will share the screen, okay?
Okay, great.
Wait a second. Okay, so I will pass the slides. Just let me know when to go. Okay, can you see it?
Okay. Not yet. Oh, it's coming now, I think. Don't loading. Maybe I should leave and rejoin.
Yeah, because I can see them changing. Maybe it's your connection. Let's move on because we are a little bit behind the schedule. So Kalman, I give the floor to you so we can start with the panel and with the presentations from the external projects. So I stop sharing my screen now and the floor is yours. Thank you so much.
Okay, hello. Thank you for the stage. So this is a panel where we're going to have several partners or actually other projects that are similar to Sodalite. I'm sorry, I don't think I have my slides on. Okay. So this session is about collaboration and synergies with other H2020 projects. And we're going to have 3 presentations from 3 projects with technology similar to Sodalite, from the RADON project, the PIACERE project, and LEXIS. Let's go straight to the topics. The first speaker is from RADON, Giuliano. Giuliano, please go on, present.
Hello everyone, you should see. Let me share the presentation. Right, so thank you very much for the kind introduction. I'm happy to present the outcomes of the RADON Sodalite collaboration, which is in particular the RADON Sodalite hybrid compute profile for Tosca. This was a collaboration that involved contributions from several Sodalite and RADON members that you see listed here on this slide. Just a few words about RADON. This is a project that has recently concluded with 8 organizations, academic and business organizations from Europe. And our focus was on serverless computing and the function as a service. And there was a strong synergy with Sodalite in terms of adoption of Tosca as the underpinning modeling and orchestration formalism. And therefore, the 2 projects decided to establish a collaboration that lasted about 6 months. The motivation for the collaboration, in addition to the commonalities on Tosca, was also to explore how we could expand the range of both projects in terms of, for example, integrating in Sodalite event-driven behavior and serverless processing, which is useful in settings like, for example, edge computing, which may still collect information that is then processed by, say, HPC facilities, but that is very diverse in terms of technologies that are required to develop and deploy edge applications compared to HPC technologies. And when you look at software engineering frameworks in HPC or cloud or edge, they are fairly diverse. And indeed, the RADON and Sodalite were fairly diverse. So for us, this collaboration was a way to also demonstrate that Tosca truly enable the possibility to essentially cooperate also at the level of tool chains and models between very diverse projects that had very different unique requirements. And the outcome, as I already mentioned, was this hybrid compute profile that brings together essentially the templates and the Tosca models of both projects in a unified solution. And this collaboration was also done through the Tosca Emerging Computer Doc committee that helped steering this joint hybrid compute profile definition. Just to give you a sense of how we applied this profile, we looked at the Sodalite Snow use case, which you have seen extensively discussed in the presentation by Piero Fraternali. And we have tried to connect this use case to a function as a service pipeline that took some of the images in output of this use case to automatically create thumbnails and show in a, let me call it a regional snow news front end these images to third parties. And so you have here a technology stack that starts from the HPC environment to produce, for example, CNN models that analyze these images to movement of the output images and also the data used by these CNN models on regular cloud VMs, and then these images are automatically moved to the FAS pipeline and shown in the front end. We also connected this front end with an edge environment with smartphones, as if users could contribute their own custom images to the front-end environment or to the HPC environment, for example, photos of the mountains used for the snow use case. And so all of this, as you see, is very heterogeneous and provides a continuum cloud use case for validation of this hybrid compute profile. What does this hybrid compute profile contains? Well, Ansible playbooks and Tosca node types for HPC, cloud, and serverless technology, ranging from open source solutions, I don't know, like OpenStack, for example, or OpenFAS, to commercial ones based on AWS, Azure, and Google offerings. You see in this image an example of the integration of some of the snow use case Tosca templates in the RADON graphical modeling tool, which is an environment that displays graphically the architecture of the software and allows directly the modeling to GRI in a way similar to what Sodalite has done in their environment, but based on a completely different solution. And this integration took just a few weeks, demonstrating the ease of the use of Tosca models in a completely different environment. We've also worked extensively on the data pipeline aspect. In particular, there was an early realization that in order to support the full use case, we needed to ensure a movement of data from S3 to the HPC and vice versa. And there was in particular need of great FTP support. And so part of the collaboration was about extending the work done in RADON on data pipelines, which are abstractions to declare the movement of data and possibly the processing of this data by serverless functions in terms of an end-to-end workflow. And we have added new nodes that allow to use grid FTP in these pipelines, as well as to SSH and do common data transfer operations that were required for the use case in question. You can find actually the results of this extension in our joint RADON Sodalite GitHub repository. You see here an example of how you can describe a data pipeline in this environment, whereby we used the NiFi pipeline orchestration solution. Is an open source solution to declare the grid FTP transfer to S3. And so you see here a screenshot of the Tosca node declarations for this pipeline. This is, of course, just a glimpse of the full solution. Data pipelines that are available now both to RADON and Sodalite are very rich. You can see here the variety of Tosca node types that are supported, as well as the various data related technologies like MinIO, which we use for storage at the edge, or Azure Blob, and also SFTP and grid FTP transfers, among others. Thank you very much for your attention. If you're interested to find out more about this collaboration, we've done a joint seminar for Oasis that is available on YouTube, and where you can discover more about these activities. Thank you very much.
Thank you very much. The next speaker is from PIACERE. Lera.
Yes. Hello, good morning. So I'm going to try to share my screen. Okay. You can see the presentation, right? Okay, so I will present the PIACERE project and the relationship of Sodalite and PIACERE. So PIACERE started last December, so we are barely 1 year old. Tecnalia is the project coordinator and XLab is participating also in the project. So the main goal of the PIACERE project is to develop a set of tools and methods and techniques that would help organizations, software organizations, to adopt the infrastructure as code approach. So we know that infrastructure as code has become more and more popular in order to manage the infrastructure as if it were a software application, let's put it that way. And we are trying to do this covering not only the development, but also the operation of this infrastructure. We're focusing on several, let's call it non-functional requirements, which is quality of the code and the models that we develop, security, trustworthiness, and availability of the infrastructural code. And the main goal is to ensure the business continuity of the infrastructure as code, or the application deployed on such infrastructure as code, by providing what we call the self-healing mechanisms, trying to anticipate to potential failures, detecting anomalies, and learning from these past anomalies. Let's say it that way. So the target users of PIACERE are developers of infrastructure as code and operators as infrastructure as code. But since we are trying to follow the DevOps philosophy, our main target users are DevOps teams. So why are we developing this project? So as I mentioned before, infrastructure as code aims to automate the deployment, configuration, and provisioning of different tasks related to infrastructure that otherwise would have to be done in a manual way. So instead of having someone just parameterizing, let's say, the infrastructure, we can do it, as I say, doing it as if it were a software application. And we have here three main trends. So one is the virtualization. The other one is the computing continuum, or the cloud computing continuum. And then the third motivation is the DevOps philosophy, or SecDevOps, or the DevSecOps, depending on where you place the security part. And then what we are trying to present, or we are trying to give as PIACERE is templates for source code, for abstractions, scripts, policies. We are going to be, or we plan to be able to model different elements of the infrastructure, not only the cloud resources or cloud services, but also other kinds of elements, like, for instance, IoT elements and so on. So which are the challenges that we are facing right now? So, or why PIACERE was born? So when an operator or a DevOps team tries to write infrastructural code, they find that they have a lot of options. So you have Terraform, you have Ansible, you have Chef, you have Puppet for different activities. So you have one that goes for the configuring, or another one that is suitable for the provisioning, and then you have the part of the deployment. So and the DevOps teams need to learn all of them and need to be able to establish, let's say, the sequence. So that's one of the main challenges that PIACERE is trying to solve. Also, some of the solutions that exist nowadays for monitoring the infrastructure and the cloud resources is reactive. So you get a failure, you react, you propose a solution. And here what we are trying to do is we are trying to predict failures or anomalies, as we call them, mainly in two aspects. One is the performance of the VM or the infrastructure, and the other one is the availability with respect to the SLAs. So how far the SLA if is going to be violated or not. And then we are also proposing several self-healing strategies. So depending on the kind of violation, depending on the issue that we have, the anomaly that we have, we will have different strategies to self-heal the application. This can go from a complete redeployment to just restarting a virtual machine, for instance. Another of the challenges that we are facing is that there's not really an end-to-end solution that covers the devs and the ops. So you have the devs teams, the ops teams, and they do their own thing. So this is why we are focusing on the DevOps philosophy. And then finally, a very important aspect is the trustworthiness and the security aspects that, as you know very well, the security aspects are usually often left for the end of the development or the end of the development. And it's not really taken into consideration beforehand. And then when monitoring, the security aspects are usually forgotten. So this is the approach that we are following in PIACERE. So we have the Devops cycle that a lot of you have seen many times. And if we start with that, so what we are trying to do first is we are trying to help the DevOps teams model their infrastructure or the deployment, the different resources that they would need, so that they do it in what we call the domain language, and I will explain it a little bit more later. A modeling language that allows to abstract all the, let's say, language related aspects. So they do it in an easier way. This way, they do not have to learn multiple languages. They just do it in using the domain language. And based on this domain language, we are able to automatically generate infrastructural code, which can be, in our case, Ansible, Terraform, or also evaluating the possibility of creating Tosca blueprints. Then we are able to verify the model and the code. So what we try to do here is to verify the correctness of the models and the correctness of the code, but also we are inspecting the security of the infrastructure as code, the libraries used, so that we do not have any kind of exploitable aspect, let's say. Then before the code is deployed on the infrastructure, we are able to simulate, or we are planning to, or we hope to be able to simulate the behavior of the infrastructure as code in what we call the canary environment, and then also optimize the deployment configuration based on several, as I say, non-functional requirements, depending on the characteristics of these non-functional requirements and what the DevOps teams want to prioritize. The deployment will, or the configuration deployment will be customized So we have here what we call a multi-objective, multi-criteria problem, in which you have multiple objectives, and you also have multiple criteria with different levels of importance. And then once we have this deployment configuration optimized, we are able to execute this deployment and orchestrate this deployment from the configuring to the provisioning to the deployment orchestration. And finally, once we are in the ops part, we're able to monitor the infrastructure as code, not only what we call the runtime properties, which is performance and availability, but also security aspects. And we're able to propose, as I mentioned before, self-healing strategies and learn from past failures. These are the results that PIACERE is going to obtain. I will not go into the details because of the time constraints